Welcome to WebEx. Enter your access code or meeting number followed by pound. Enter your attendee ID number followed by pound.
Okay, can you guys hear me okay?
Yeah, now I can. Yeah,
Okay.
I had myself muted too. I couldn't figure it out.
Okay, no problem, guys. Okay, we'll try to go through a little bit of chapter 2. Now, I sent this to the lab class as well. If you guys have any questions over the microscope, but this is really something we're not going to be able to do a whole lot with remotely. But we can go over this and try to get, let's see, we can get to about 30 slides. I'll be thinking we're doing good. I am recording this, so if you guys need to hear it again, and of course we got the videos. Okay, let me get this guy going. Okay. So the biochemistry, again, a lot of folks have trouble with this because it is something they're maybe not familiar with. And okay. So this is just a bunch of definitions. And definitions happen to be one of the favorite things for the guys that write those test banks. So you might want to kind of focus a little bit. As far as matter, matter is just the physical things around us and everything around us. They define it as has mass. Mass is more or less equal to weight, and it occupies volume, space. Now, there's more than 3, but we only care about these 3 for our purposes. It can be a solid, a liquid, or a gas. And each of these are slightly different than the others. A solid has a definite shape that does not change by itself. It occupies a certain amount of volume. That's what, really makes it that. Now, liquids has a certain amount of volume. If you've got a gallon jug of milk, it's going to be a gallon no matter what you pour it into. But the difference between this and the solid is it's going to take the shape of whatever you pour it into. You pour it into a square bucket, it's going to be square. A round bucket is going to be like a cylinder, whatever. Now, gas is just totally different than both of them. A gas is going to be like a liquid in that it's going to have whatever shape you're holding it in. But unlike a liquid or a solid, the volume, the amount of space gas takes up, just depends on how much you compress it. And we know that gas is compressed. We've seen these tanks that folks have. You can take gas and squeeze it into a smaller volume, which you can't do with the other 2 guys. Okay. Energy is real complicated, but we're just going to keep it super simple. As far as we're concerned, there's only 2 kinds of energy. There's energy that's kind of in motion, kinetic, and then there's potential energy, which is kind of stored. Potential energy, the easiest way to relate to that is to think about the battery in your cell phone. It has stored energy. As you turn your cell phone on and those electrons move, the kinetic energy. Or you could think of it like this. Wile E. Coyote, when he's after the roadrunner, always has an anvil hanging up over the road. That's potential energy. If you cut that rope, that anvil falls. When it does fall and hit the coyote on the head, that's kinetic energy. How's that, guys? Is that reasonably clear? Matter and energy?
It works for me.
All right. Well, we're good then. We'll keep going. Energy comes in different forms. Chemical energy, which is what we have with our batteries. Electrical energy, which are charged particles like electrons moving through the circuits. Mechanical energy, which is things like something falling from a height, like a landslide, or something like that, or an automobile accident. When the vehicles come together, they're moving at a certain speed, kinetic energy, but as soon as they stop, they're going to have that crash and all that energy is going to be kind of reflected back to them. And then we got the radiant, the electromagnetic. This is, it's magnetism, but for our purposes, it's also light. The visible light we can see with our eyes, the UV light, infrared light, which on all our remotes, and then X-rays that we use to visualize things inside a patient without being too awfully invasive. Okay. Yes, I'm sorry. I couldn't hear you. I'm getting an echo. Well, now guys, if you have a question, you can also type it in the chat. Okay, I can't see the chat right now because I'm sharing the PowerPoint, but I will answer all those chat questions. If you're having trouble with your audio, I have no preference. You can do either one. Okay, law of conservation of energy. We've kind of all heard about this. It states that you can't create or destroy energy. You can only change it from one thing into another. We do that. I mean, we've got dams on the rivers. The water that is higher up than the river below the dam is falling, so it's going to be mechanical energy. It turns that turbine, again, mechanical energy, but the turbine with the wiring and the magnets is going to generate a current. So we change it from mechanical to electrical. That's easy. Problem is that we always have a huge loss. We lose a lot when we convert. We've got LEDs and the other lights now, but the old incandescent bulbs only converted a fraction of the electricity into light. The rest of it was heat. If you've ever had to change one of those bulbs, you know. Now, human beings and other animals, we actually have an amazing efficiency. We turn about 40% of our blood sugar into energy. The other 60% is heat. It's wasted. We use it to keep our body. Engineering things, 10, 15, 20% is considered humongously effective and very efficient. Periodic table. We're not going to do a whole lot with this. It's not a chemistry class, but there's some things about this that are kind of interesting and it will be the way they've got this arranged. Okay, there's Well, never mind. I need to wait and go over this after I go over the electrons. Okay, on the table, they're set up with these little squares. Up there, they're going to have the atomic number. The atomic number is the number of protons that are inside the nucleus. That's what makes something aluminum or carbon or gold or chlorine, is the number of protons. Now, for our purposes, that's constant. You can do this, change it with nuclear reactions, but that's not really applicable to healthcare. So for our purposes, we'll just consider these things constant. They don't change. That's what makes one element an element. They always give a shorthand, a symbol. Carbon is C. What happens when you come up with another one like chlorine? Well, just add that L. And some of them make no sense at all. Sodium is Na. Well, it does. Natrium is the Latin word for sodium. So some of those that were known back in the day, Fe for iron, the ancient people knew about those, so they named them, and we just kept the name. Okay. 1, 2 letters. There are some 3-letter ones, but there's some of these that go, this one is pretty straightforward, but they've got like 115, 120 of these, whatever. And some of these only last a fraction of a microsecond before they break apart. And that's not something we're interested in. Okay, the atomic weight. If you have carbon, you have 6 of these protons. Oh, let's just go to the next one. It'll be easier to show you. So here's how we see our atomic models. This is the one that's really closer to the truth, but we don't need that. So in the nucleus, you're going to have protons, these red guys. That's 2. 2 protons is helium. That's it. Normally, helium will have the same number of electrons as it does protons. Now, here's the thing. A proton has a +1 charge. An electron has a -1 charge, so they balance each other out. But the fact of the matter is that proton is 2,000 times the size of the electron, but that don't matter. All that says is that the electron doesn't add a whole lot to the atomic weight of these guys. Now, here's something we hadn't talked about yet. Not all elements have these. I mean, most everything from helium up. But there's also things called neutrons. They're the same size and weight as a proton, but they have absolutely no charge. For what we're doing, we're mostly concerned about the electrons, because that's going to cause things to react and rearrange themselves. But we'll see that coming up. Okay. AMU is just, remember, carbon was 12, and there's some other numbers in there, and we'll talk about that. But that's basically because they have 6 protons and 6 neutrons in the nucleus. 6 and 6 is 12. That's easy. There's 6 electrons out there, but they don't add much to it. Okay. But this is good if you just need to refresh your memory on it. Okay. This is why you got all these weird fractions on these weights. This is the normal form of hydrogen. It has 1 proton and 1 electron, and that's it. That's hydrogen. Probably about 95%, I'm making these numbers up a little bit, but the overwhelming majority of hydrogen is going to be just like this. But there's variations. There's a one form of hydrogen that has a neutron, still only has one proton, because if you don't have one proton, then you're not hydrogen. This guy's called deuterium. It's radioactive because this is not stable. And then there's another form that's even more radioactive. It's called tritium. One proton, but this guy has two neutrons in them. Those are called isotopes. So if I were to make a guess, and that's what I'm doing, I'd say this is probably the breakdown of these guys. I mean, and I'm probably overestimating them. Tiny, tiny fractions, but they're not zero. So if you had a cylinder full of hydrogen gas, the atomic weight is going to be equal to 95 times 1, because there's only one, 4 times 2, and then 1 times 2, or excuse me, 1 times 3. That's how they come up with it. So they add all these together, and then they divide it, and it comes out to these weird things like this. Carbon is normally carbon 12, meaning 6 protons and 6 neutrons. But there are some that have extra neutrons, and that's what's going to make one of these guys what they call an isotope. Carbon 13, and there's an even rarer form called carbon 14. You guys may have heard about it. That's what they use to date like dinosaur bones and rock sediments and things like that. But that's pretty much, well, the only isotope that I can think of that we really focus on, unless you're in nuclear medicine, is iodine, which we use to destroy the thyroid gland when it's maybe causing problems. It's easier to fix if they have hypothyroidism. Okay, the radioisotopes, these guys just naturally break down because they're not stable. They can do all this. This is not really. Problem with radioactive things, these guys actually, and that's why people can get radiation sickness. This stuff's going to hit your DNA and cause damage, and that damage can cause your DNA to start making cancer cells. But they do use some radiation against cancer cells. Radon, uranium decaying down in the earth, and we're bombarded with radon. There are folks that make a living trying to shield it. Maybe there is a reason for it. For the most part, there isn't. There's a background radiation. We're all exposed to it. Most of lung cancer is going to be caused by another more easily controlled thing like cigarette smoking. Okay, overwhelming everybody, or is it making a little bit of sense?
It's been fine so far for me.
Okay. So now we're going to talk about how these atoms by themselves hardly ever exist. I mean, there's some, but most of the time, these guys are going to react with other atoms and form a molecule. And if you guys remember from chapter 1, this is our next step up in the organization of human beings. So there's hydrogen with 1. There's helium with 2. Helium is absolutely stable. Helium gas doesn't blow up like hydrogen because it turns out that in the first orbit, and they call these shells, by the way, in the first shell, if you've got 2, you're stable. Helium is super stable. Hydrogen is very flammable because he needs one more to be stable. Now, what happens a lot, and this is what in the atmosphere and maybe outer space, what happens is you get two hydrogen atoms together and they share their electrons so that each one of those guys kind of thinks he has two, and it makes them more stable. Of course, they are explosive. It's not the most stable. Now, that's for these guys. Now, when we get up to carbon, remember we had 6 electrons? We always have 2 in the innermost shell, but the outermost shell can hold 8. Carbon has 4 there. Neon, which is like helium, thing. Carbon needs 4 more. So what's carbon going to do? Well, a lot of times, this guy with his 4, he'll find 4 hydrogens, and these guys will share like that. Not very stable because that's methane, and it's explosive too, but that's how these guys want to get to a stable place. They want to share an electron. And not all of them don't do this, but this is the main thing. But here's the thing. On carbon, those 2 on the inner, they don't count for nothing. They have nothing to do with this guy's reactant. It's only the ones in the outermost shell. And needless to say, there's a 3rd shell and a 4th. We're not going to get too much more into that, but it's always the outermost shell that's going to be the one that causes a guy to react. The ones in the other ones are not going to be important. Now, after that first shell, almost all the others are going to be 8, and they call that the octet rule. All they're trying to say is that every atom needs 8 to be stable in that outer, after you get past helium. Okay, let's continue on. We already said this, elements, you can't break them down chemically, you can only do it in a nuclear reaction. And each of these has their own characteristics. Nobody is going to confuse sulfur and gold. They're 2 totally different. And it's all because of those protons in the nucleus. The chemical properties, that's all about those outermost shells. They call it the valence shell. Here's an example. Well, hydrogen needs 1. Helium is perfectly fine. I'm good. Lithium has 3. So this guy needs 7 to get stable. That doesn't sound real easy to do. We'll get into this in just a second. It's going to get stable, but it's going to use a different thing besides the sharing. Yeah, we'll wait till we get to that. Here's some more terminology, guys. Anytime you get 2 or more atoms that connect by sharing electrons, you've got a molecule. Now, there's a special kind of molecule that's called a compound, and the difference between this and a regular molecule is that, remember that H2 I showed you, those 2 hydrogens? That's a molecule, but it's not a compound. To be a compound, it's got to have 2 or more different atoms. So H2O is definitely a compound. It's got 2 different atoms or 2 different elements that are bound together. Okay. This is the part that is somewhat confusing for a lot of folks, and I can absolutely understand it. You really have to work to get your head around this stuff. There's a thing called a mixture. Now, a compound like H2O, these guys are sharing electrons and they are bound together. I mean, you can run electricity through water and you can smell the oxygen and hydrogen coming off of there. You can break it that way, but they're pretty much well stuck. A mixture is when you got these guys and they just happen to be in the same place. So salt water, which is what we're made of and what the oceans are made of, have a lot of sodium and chlorine, and they're mixed in with the water, but they're not bound to it. Not the way we've been talking about. So this is like physically intermixed. If you took a shaker of salt and took a container of sugar and you mix them together and stirred them up, that's a mixture, but they're not bound together. How's that, guys? Does that make a little bit of sense? Hopefully.
Yeah, it's making some.
Yeah, it's now there's mixtures can be one of two kinds, homogeneous or heterogeneous. So if you were to take a glass and dip it in the ocean, you would not be able to see the salt. The salt doesn't fall to the bottom. You know, it's mixed in there and it's basically evenly spread apart. So you're going to have the same amount of salt no matter if you were to take a drop from here or here or here, you're going to have the same amount of salt. That's homogeneous. It just means it's evenly distributed. Heterogeneous is when you put something in there and it doesn't. It just basically falls to the bottom. If you tried to take sugar and put it in a glass of cold water, I mean, you could stir it and it would be swirling around, but sooner or later, all that sugar is going to wind up on the bottom of that glass. That's heterogeneous. There, you'll have all your sugar in one place and no sugar up there. How about that one? Some more terminology. Now, we've actually classified three kinds of mixtures: solids and colloids, and solutions and colloids and suspensions. And we'll go over those one by one. Okay, this is just, compounds are always homogeneous because you're always going to have these guys in the same ratio. We already talked about that. It's good information. Homogeneous, when you see something that's homogeneous, it's usually going to be see-through. I mean, it may be a little cloudy, and there's stuff in ocean water we know besides just salt and water, but it's going to maybe a little cloudy. It's transparent. You can see right through it. Now, on a solution, you got two things. You've got the solvent and the solute. And the way you define those is whatever you have the most of is the solvent. Whatever you have the least of is the solute. Now, in ocean water or human tissue fluid, usually you got more water and you've got less salt. But here's the thing, guys, if you were to take an eyedropper of water and dump it into a salt shaker, but the water would be the solute. It's just whatever you got the most of. Most of the time it is going to be a liquid for a solution, but it doesn't always have to be. Okay. Excuse me. Here's something that we really got to wrap our heads around, because this is going to be super, super important. AMP1 and especially AMP2, concentration. Turns out that if you were to get some ocean water and you were to measure it, you would have exactly 9/10. Didn't mean to get a box there. 9/10 of 1% of that ocean water is salt. And that's exactly the same ratio we have in our body. We call that normal saline. When we give the IV fluids, that's normal saline, 0.9%. There's lots of ways of talking about this concentration. Milligrams per deciliter, that's what they usually do with blood sugar, with glucose. We know about 100 is a pretty good normal if you're not, in the fasting state. You can also do it in molarity or moles per liter. That's kind of a technical thing. Can't see us doing a whole lot with that. And I'll get down to this thing right here, but concentration is super important. There's a certain amount of sodium in our body, and that's called something called osmolarity, but let's just forget the unit. Let's just say it's about 150. And there's another 150 just about that is chlorine, because we get salt, right? Sodium and chlorine. And that's our normal. That's the way our system likes to work. What happens if I get dehydrated and I lose water but not salt? Then the concentration goes up. And that's lethal to us. Hypernatremia. What happens if, like those folks on those radio contests, I drank a lot of water in a short period of time? Well, if you add water but you don't add salt, the concentration gets less, right? And then you die from hyponatremia. They're both equally fatal. But this is why concentration is so important. If our main we call them electrolytes, sodium, chlorine, magnesium, calcium, potassium, if these guys get out of whack, we're in a world of hurt, either high or low. We're in that, going right back to it, we're in that small range. And that's where we have to stay. About this. That atomic weight, we said the atomic weight of carbon was 12011, and that's just an abbreviated form. But here's the thing. If you were to get 1 mole of carbon, it would weigh 12.011 grams. What's a mole? That's a mole right there. Avogadro's number. 6.02 with 23 zeros behind it. That's a lot. But every element is a mole is a mole no matter what it is. A mole of hydrogen would be about 1 gram. Because hydrogen's atomic weight is just a little over 1. And heavier things like lead, uranium, they would have grams. But we're going to try not to get into that. Okay, colloids. These are also called emulsions. These guys are usually going to be heterogeneous. You can kind of sort of see a little bit through them. Jello is a colloid. They're large particles, but they still don't fall to the bottom like I said the sugar would. It's going to be, they're larger, and they do kind of tend to collect in an area. That's a colloid. Jello is probably the easiest one to remember. A suspension, this guy is absolutely heterogeneous. And the best example of one of those is going to be blood. Now, while our heart's beating, our blood's moving, and the things kind of stay, moving. But when a person passes, the heart stops. The blood is no longer being pushed. All those red cells and all those other things fall to the bottom, just like the sugar we talked about. And of course, we know that this one is definitely not going to be see-through. It's going to be opaque. I think I've got a good thing. Yeah, here they are. Mineral water, salt water, whatever. Small particles, and since the particles are small, they don't enter the light waves, but you can see through it. Colloid, larger particles, not necessarily evenly spaced, and they're going to be semi-translucent, I guess is the easiest way. And in the suspension, you got big particles, and if something doesn't keep them moving, they'll just fall to the bottom. Ooh, wait, how was that? Is anybody crying for their mommy yet? Hopefully not. It's tough, guys. I'm not making light of it. It's something you have to spend. And I'll be glad to, we can set up WebExes anytime, not just on winter storm days. And I've got Tuesday and Thursday afternoons that I can help you guys with this. So try your best to look at it. Look at some of the videos, some of the other videos besides mine. And if you still have any trouble, get with me and we'll talk about this. Okay, we're back to the bonding. The octet rule we've already talked about. That's the thing that drives these guys. Hydrogen and carbon. There's oxygen. Oxygen has 6 electrons in its outer shell. It needs 2. Now, the closer it is to being stable, the more reactive the element is. That's the reason oxygen burns and blows up. It's because it needs 2 electrons, and it's not afraid to go out and make a mess getting them. But even worse than oxygen is chlorine. Chlorine has 7 in its outer shell. This guy is super desperate. That's why chlorine is so toxic to us, because these guys are going to grab an electron and they don't care where it's from. And here's sodium, which usually goes with chlorine. Now, if you notice, this guy's got 2 on the first, it's got 8 on the second, it has a single 1 on there. And we kind of talked about that. This guy needs 7 electrons to get stable. I don't see that happening. How's this guy going to get stable? Well, you remember chlorine over here that has 7? Here's what they do. This guy actually transfers his electron to chlorine. Now he's got 8, he's stable. Chlorine's got 8 and he's stable. There's a problem with that though, and we'll get into that. So when we absolutely just, here, take this electron, that's going to be what happens with sodium and chlorine. But look, chlorine or sodium, he had, let's see, we've got 2, 8, 10. So this guy's got 11 proteins. He had 11 electrons. Now he only has 10 electrons because he gave one away. So that means sodium now has a +1 charge. Most atoms are neutral, but when you lose an electron or you get one, you've changed things. Chlorine now has one more electron than it does protons, so it has a -1 charge. Positive and negative attract each other. So that's why sodium and chlorine get together and make salt. Now, this bond that these guys make is pretty weak. You put it in water and they separate, but they're still there. That's the ionic bond. It's where charged particles just are attracted to each other because of their opposite charges. Now, we talked about the sharing bond. Turns out you can share in two ways. Share equally, or one can get more. Let's look at one where one gets more. Here's oxygen. So this guy needs 2. Here's hydrogen. He's got 1. Here's another hydrogen. He's got 1. So they share. Here's the thing. That hydrogen right there is only pulling with 1 proton. He's got 1 plus. This oxygen is pulling with 6 protons. So that electron is not shared in the middle. It's going to spend more time near oxygen than he is near the hydrogen. Because he's going to spend more time near the oxygen than the hydrogen, this guy is going to have not a +1 charge like sodium, but he's going to have a fractional, partial charge. And then they use a little Greek letter to do this. So he's got a partial positive. Now the oxygen is doing the same thing with the other hydrogen over here. So he has a positive or partial positive. Now, the reason oxygen can get away with that, well, the more protons you have, the more pulling power you got on electrons. They call that electronegativity. But if you look down here, you'll see that water molecule is kind of bent like this. But let's look at CO2. Now, CO2, oxygen has more protons than carbon, but they share equally. The reason they share equally is that this oxygen is pulling this way and this one is pulling that way. It's like if you had a tug of war with each side absolutely equal. Which way would the rope move? It wouldn't. It would be taut, but that's it. So not only does this depend on how much pulling power they have, it also depends on the geometry. These guys are pulling exactly in opposite directions, so it's just stable. Now, these little lines here, that line means that these guys are sharing 1 pair of electrons. When you see these double lines, it means these guys are sharing 2 pairs. Because remember, carbon needs 4, but oxygen needs 2. So this is the way they do it. We call the sharing bond covalent. Covalent comes in 2 flavors. They share unequally, polar. They share equally, nonpolar. These guys are going to be pretty strong bonds. Okay, ionic bonds. These guys transfer. Here, take my electron, please. The guy that gains the electron is going to have that negative charge. Here's his name, anion, a negative ion. Any kind of charged particle, like an electron, which has a negative, or a proton with a positive. So the sodium is going to be a cation because he has a positive charge, and the chlorine is going to be an anion, and the mnemonic is a negative ion. Anion is negative, so the other one is going to be positive. We talked about these guys being molecules because you really need the covalent bonds. They make crystals in which these guys are stacked on each other. And you've seen salt crystals. I mean, they're small, but you can look at them in your table salt and see those. Here's sodium giving up his electron. There's chlorine taking it. Sodium is plus now, 1, and this is negative. Here's what the salt crystal looks like. So the big ones, the big green ones are chlorine, and the small yellow ones are sodium. Because these guys are charged, this guy's got a plus charge, so all of these chlorines are going to want to be around it. And right there in the middle, this guy's going to have 5, and ones in the bottom, you'll have 6. These guys will have these guys on every side. There's the sodium and these. You do that? Yeah, that's right. But anyway, that's the crystal. But as soon as you put these guys in water, they're going to break apart. This is going to be kind of important for some of the stuff we're going to be talking about later. Here's the thing. Remember I told you that oxygen has a partial negative and hydrogens have a partial positive? So I'm just going to draw these like this, make it simple. So these guys are going to attract, this guy's going to attract the sodium because oxygen has a partial negative. These guys are going to attract the chlorine. And that's how water dissolves salt. It actually, those ionic bonds are not as strong as the covalent, so they just let go. And water kind of surrounds them on every side. And that's how we get that solution. Water is called the universal solvent because more things will dissolve in water than anything else. And it's all because of those charges. Okay. We're going to find a place to stop here in a minute, guys. I know a little of this stuff goes a long way, but I would want to try to get at least a third of this knocked out. Covalent, we share equal or unequal, depending. And here's our definition. Atoms that have 6 or 7 shell electrons are going to be electronegative. They're going to tend to grab electrons. Those with 1 or 2 are going to be electropositive. They're going to be tending to give them up. And that's how we get those. Oh, let's see, a little bit more. So there's our 4 hydrogen atoms. We already talked about methane. And you can see these guys sharing them. And so carbon sees itself with 8 electrons, and each one of those hydrogens sees themselves with 2. And because of the geometry on this guy, there's no partial charges. Carbon tends to be an equal sharer. That's one of the reasons all of our body chemistry is based on carbon. Let's go here. Now, oxygen also, and I'm sure everybody's heard the word O2. So you get the oxygen with the 6. I'm sorry. Yeah, that's right. With 6. So we're going to put those on there. And there's the next oxygen. Am I doing that? Kind of, sort of. 2, 4, 5, 6. Yeah, I did. So this guy's got another oxygen. This guy's going to see himself with 8 because he's going to share a pair of electrons. And if you remember, that's that guy right there. And that's the oxygen we breathe in. That's the oxygen we give our patients. Let's see. We're almost to the end, guys. Hang in there. I know this is a lot of stuff. Nitrogen, on the other hand, has 5 in its outer shell, so it needs 3. So the way these guys do it is they share 3 pairs each. And this is the way nitrogen is in the atmosphere. These guys, since they're sharing 3 pairs, they've got this triple bond. And we've already talked about this, that the oxygen is going to pull a little bit more toward itself away from these. We've already talked about that. Now, this is why, and I know everybody's seen it, you can feel water just a little bit over the rim of a glass. And you've seen those water striders, those little bugs that walk on the water. You've seen water bead up on your car windshield because these guys, even without the sodium or the chlorine, these guys are attracted to each other. So this partial negative on this oxygen molecule is attracted to the hydrogens on the other molecule. And this is another kind of bond. It's called a hydrogen bond. And we're going to see a lot of that later on in this chapter. So this is really important. And it's weak. It really is. And yet so much of our body chemistry depends on this weak bond. Okay, guys, that's 33 out of 91. I think that's enough. Has anyone got any questions about anything? Because I don't want to leave anybody hanging. Are we good, guys? Questions about anything? And since this is for lab 2, I'll be glad to talk to you about anything on the lab. What you think? Do I have the... Oh, there's the chat. Okay. Yes, what I meant was that this is going to be the same one for the lab class. We can't do a whole lot in here since we're supposed to be doing it on microscopes, but I'll be glad to go through anything you guys have any questions about. And if you don't have any questions, I think I've done enough for one day. I don't want to put a lot of stuff in your head. I don't want to make it overloaded. Now, this is all I got, guys. What I'll do after the meeting is I will, I'll get the recording and I'll upload it to the 2113 playlist on my YouTube channel. So if you want to go over it, of course, I've got the video that goes with this PowerPoint. It's already on there. So and we ran almost the exact time of our class. That's good. Any questions at all?
That I can think of.
I'm sorry, I couldn't hear, sir.
I said none that I can think of.
Well, that's it, guys. Now you can, if you come up across a question, just shoot me an email. I'll be checking my email all day long, and I'll email you back an answer. And if that's not good enough, I'll set you up a personal WebEx, and we'll go over anything you guys have any questions about. Okay, let me stop the recording.